Hello, everyone. Today I will introduce the paper named Expert Level Detection of Pathology from Unannotated Chest X-ray Images, where self-supervised learning. The problems that this paper tries to solve is that although current models for medical image interpretation tasks, such as disease diagnosis, which is basically a classification task, can match or even outperform the medical experts. However, most of these models require large labeled dataset during training, which can be expensive and time consuming because those labels for the dataset requires expert knowledge. So in this paper, they choose a specific task. They hope to detect the pathology from chest X-ray images, but without annotated labels. Before their work, they mentioned several related methods. All of them are so-called label efficient methods, which means they didn't require a fully labeled dataset during training. However, label is still required at some stage of the network, maybe the inference or maybe the fine tune. All these three mentioned papers are based on the contractive learning, but they have different settings. For the first methods, they do contractive learning with augmented images, which is basically follow the idea that with the same image but using different augmentation methods, they still needs to be very close to each other in the latent space. The second method is still contractive learning, but with a pair of images from the same patient. The hypothesis behind that is that for same patient, if the time interval is short enough, the images from the same patient should be very similar. They should fall into the same class. The third method, it's still contractive learning, but this time it's multimodal. They contractive learning between pair of images and radiology reports, which is a text information, but they randomly sampled sentences from radiology report. However, there's still some remaining gap for these label efficient methods. The most important thing is that label is still needed for specific task. And the second problem is that the prediction ability is restricted to annotated diseases. So you can imagine that if we have a data set, we have a small label efficient data set for cancer, for chest cancer, then the model will be able to classify the cancer, but will not be able to classify other diseases. So to fill the gaps that I mentioned, the remaining gap that I mentioned in the last slide, they proposed a new method called the CheckX0, which is still based on contractive learning, but using a different setting. They used the checks X-ray images and their corresponding radiology report. Because for each chest X-ray images, they naturally came with a radiology report. So there's no specific require the procedure to get the label, but the radiology report itself already contains the description and also some classification information of these X-ray images. So we can, by using the contractive learning, we can already learn a meaningful encoder for the image as well as for the text for the later the classification task. So as you can see in the left part is their pre-training part. they will provide a pair of X-ray images and their radiology report to the vision transformer, which is a vision encoder, and the text transformer, which is a text encoder, to the latent space, and using contractive learning to distance in the latent space is as close as possible. One more thing to notice is that the vision transformer and the text transformer here, they use the OpenAI's CLIP pre-trained model directly. So what they do is actually using this radiology image and text to fine-tune the CLIP. For a specific classification task, for example, if we want to classify if this X-ray has cancer or not, they proposed this pathology classification framework, which is basically given the text transformer a pair of positive and negative prompt. Basically, it's telling that this chest has cancer, or this chest image has cancer, or this chest image does not have cancer. They give these two prompts into a task transformer and calculate the normalized similarity between the output of the task transformer and the vision transformer given these two prompts. And they comparing this normalized similarity, if no cancer is higher than has cancer, then this chest image is classified as has cancer. So this is their framework for the classification. And the good part of this classification framework is that they overcome the problem that previous prediction ability is restricted to annotated diseases or some specific diseases. However, for this classification framework, you can provide any kinds of classification task through this text prompt. And one more thing to mention is they use the knowledge distillation procedure, because as I mentioned before, this method also using a pair of images, but the text part is different. They randomly sampled sentences from the radiology report. This is because that CLIP and other kinds of similar text transformer at that time cannot have a very long sentence. The longest number of token for CLIP is 77, which is too short for a radiology report. So to overcome this, they first trained the model with the impression part of the reports, which basically is the most important part of the report. And then after they trained this text encoder, they then use this trained model as a teacher to train another text encoder with 512 maximum token, which is basically most of the time they can cover the full part of the radiology report. And how they do this teacher and the student training is that they minimize the mean squared error between the logics of these two encoders. This is a typical setting of the knowledge distillation procedure. To evaluate their proposed model, they performed the classification on two test datasets. One is called a CheckSpert, and the other one is called a PAD-CHEST. These two tasks, they are all classification tasks. The first data set, they try to classify all the images into 14 conditions. And the second one, they try to classify them into 19 different diagnoses. And for the evaluation metrics is basically the standard metrics for the classification task, such as an MCC, F1, and AUC, which is the area under the curve. Here, so they first compare their result with 3 radiology experts. They want to prove that their proposed method, even without any annotation, they can achieve comparative performance comparing to experts. So as they report the MCC and the F1 for their model as well as radiology expert. And they also report the AUC for the model because it's impossible to calculate the AUC for the radiology expert. So as you can see here, the difference between radiologists, the mean of the radiologists, and the chest X-ray is very small, which implies that their model has expert level classification performance. And then they also compare their model with the 3 self-supervised methods that they mentioned before, as well as 2 supervised methods. As you can see, based on the AUC, of course, supervised methods still outperform all other self-supervised model. However, their model is very close to the supervised model's performance, and their model outperformed all self-supervised model, even when some self-supervised model requires some label. Like for example, for this model, if they only use 1% of the label, the performance is way worse than their model. Even when they use 100% of label, their mean AUC is still worse than the new model. So so in conclusion, this paper proposed a self-supervised framework for the chest X-ray image diagnosis. The advantage of this paper is that this framework actually can easily be adopted to many other medical image applications because all these medical images applications, all these medical images will come with some kind of medical report. Like for example, for CT, they will also have a very sophisticated science report for the CT as well. So this kind of label or annotation is always available. So their methods can be applied to a lot of other applications. However, there are several limitations for their task. The first limitation is that label is still needed, but it's only in the validation process, which is on this part. When after they calculate the normalized similarity, they will use the performance in the validation dataset to determine some hyperparameters, such as the standard to distinguish between the negative and the positive. So label is still required in some part. And the second thing is that this is just a limitation. In this paper, they only evaluated the model's performance in the classification task. However, as you might know that the radiology report contains much more information than classification. For example, they might tell you that the chest X-ray has cancer or not, but they also will tell you that the cancer is in some position of your chest. And you can actually use this position information to do some unsupervised segmentation task. which is also a limitation of their current research, but can be further researched using their model. Thank you. I think that's all my presentation for this paper.